Уважаеми приятели на математиката, уважаеми колеги, скъпи ученици, днес продължаваме с третата лекция от серията от лекции на френски математици с известния френски математик Cédric Villani. Искам само да ви припомня, че нашата програма продължава. Cédric ще посети Софийската математическа гимназия утре, сутринта, и ще се срещне с ученици и учители там. А след обед имаме втората лекция на професор Патрик Попеско-Пампо. В петък, да ви напомня, всички вие сте поканени на дискусията във Френския институт от 3 часа след обед, която ще бъде една свободна дискусия за мероприятието. Ще извличаме уроци за бъдещето и нас много ни вълнува вашето мнение, особено на учениците. Какво можем да подобрим, какво можем да направим по-добре за бъдеще. А сега бих искал да представя академик Юлиан Ревалски, който е директор на Международния център по математически науки и който ще представи нашия лектор тази вечер.
Bonjour Cédric. I will change in English because we have guests from France, not in French because maybe French is a popular language here, but maybe not so much as the English. And it is my real great pleasure to present Professor Cédric Villani. I'm doing this for the second time here in this hall. The first one was 7 years ago when he visited our academy and he gave a lecture also mostly devoted to young people at that time. I remember that here the hall was full of young people. Cédric Villani is one of the most known French mathematicians. He, after being in Lycée Louis-le-Grand, he did École Normale Supérieure in Paris, and then he did his PhD degrees in University of Paris-Dauphine under the supervision of Lyons. This is another very well French mathematician who was awarded the Fields Medal. And he has been director of the Institute of Henri Poincaré. He is a professor at the University of Lyon. And he was awarded, probably most of you know, Fields Medal in 2010 for his works in statistical physics, statistical mechanics, and Boltzmann equation. His main area of research is partial differential equations, mathematical physics, and related fields. And he is a member of the French Academy of Sciences. Maybe I'm missing something, but let me add that he was also a member of the French Parliament, being involved in one of the most important issues related to contemporary science like artificial intelligence, and also very important thing that he values a lot, and this is all the things related to modern education, and which probably will be part of also his talk today. He is also co-supervisor of a Fields medalist. Alessio, who was awarded the Fields Medal in Rio de Janeiro. So I'm sure you have a lot of things to learn from Cédric, who, as I mentioned, was a student of a Fields medalist, and he is also a supervisor of a Fields medalist. So, Cédric, the floor is yours.
Thank you very much. Okay, my friend, it's a great pleasure to be here back after a few years and see that there is still this enthusiasm here for science, which is warming my heart. We'll talk about stability. I said from Newton to now. In fact, I will go back in time a bit earlier than Newton to talk about stability, but Newton is because at the time of Newton, it was the start of a new era in science and mathematics, and that new era involved the field in which I did my PhD and then my career. namely the field of differential equations and by extension of the field known as partial differential equations. A field in which you try to study and predict the world by analyzing equations bearing on differentials, which are variations. This was a giant leap in science and in knowledge of the world. Einstein himself considered that this was the single most important step which had ever been done in science. The idea that you can understand issues about the world by studying and solving these differential equations. But at the same time, it's the birth of mathematical physics. This idea that you can study the work of physics and putting it in theorems, in problems which are set in mathematical language, and going hand in hand the mathematics in the physics. Of course, it was not just Newton, there was a contemporary like Leibniz and Huygens and Bernoulli for differential equations, and birth of mathematical physics, we may say it goes back to Galileo, even though Galileo was not really a good mathematician, but he had this really impulse and enthusiasm for the idea that the mysteries of mathematics will lead us to understand the mysteries of physics. I did my career in these partial differential equations and in mathematical physics, even though when I was a high school student, I was not so much attracted by physics and not so much attracted by differential equations and analysis in general. But then you never know where eventually, which field of science you will fall in love with. And it happened that when I was 20 years old or so, and I started my PhD under the supervision of Pierre Lyons, indeed, the decision that I would work with him was just before he got his Fields Medal in Zurich. And it would have been a complete surprise for me a few years ago if somebody had told me you will work on mathematical physics and all the issue of physics. It certainly was a surprise for my physics professor when I was in class préparatoire in Louis-le-Grand, who saw that I was not at all at ease, in particular in thermodynamics, and later I made a research career in fields strongly related to thermodynamics. Life is full of surprise and so on. Let's talk now about this stability. So these are, I took back a conference which I gave for public audience in French, but I will translate whenever there is need from French to English. And anyway, the illustration will be mainly about images and things from culture, and I will have very few formulas. On just a few occasions, I will use the whiteboard here to go just a little bit into the technique. Let's start by saying what will be the subject. The subject will be stability, and the subject will be the cosmos, like the stars, the planets, whatever. We have to remember that astronomy has been a driving force for mathematics from the very beginning. I mean, from the time of ancient Babylonian mathematics and so on, 4,000 years ago, there was already the association of astronomy and mathematics. And at the time of the ancient Greeks, astronomy was counted within mathematics. It was called the mathematical art in the time of Plato and others. They really go hand in hand. But also astronomy has a special status within sciences because it's a science which is very much popularized, has a strong impact to the society at large. Every child at some point, I guess, interested in science had a moment in which she or he was interested in astronomy and what the stars, the planets, and so on. I remember as a kid, but that was at some point, that was my passion. Then it was out, then in, out again, what knows. This is a famous painting by an English painter, John Wright of Derby, middle of the 18th century, which is one of the first important descriptions of science done not by professional scientists, but science inside the home. These are here, you see a family with kids and so on, and there is a philosopher, so a scientist, giving a lecture on this orrery. Orrery is this mechanism, a planet Earth, on which you have the movements of the planets which are associated by mechanisms. By the way, the most ancient trace that we have of such a mechanism, with something like clock-like mechanism to reproduce the patterns of planets and so on, is this very ancient mechanism known as the Antikythera machine, which is something like 2,000 years old, which was discovered by accident by some divers near some island in Greece. And it was a total surprise when it was discovered to realize that ancient Greeks already had such mechanisms, a skill which was lost for more than 1,000 years after the Greeks. It took more than 1,000 years before we were able to build again such mechanisms. Yes. The ancient Greeks had a big problem when trying to describe the motions of the object that we see at night, because there seem to be two very different types of objects. On the one hand, there were the stars, and stars, if you follow them all around the year, they will have a very nice kind of circular movement. On the other hand, there were the planets. And for the planets, it is very different. They go this way, that way, this way. In particular, if you try and look at the motion of Venus, it draws some kind of flower, the trajectory, with 5 petals, and it's like a very intricate flower, etc. And the planets, they had these complicated patterns. So they only knew of 5 planets in those days, but these 5 planets were like a challenge. And they were like going in, and they were calling them the erring, like the stars which wander, like going in a bizarre way. And they had this vision that whatever is in the cosmos has to be perfect, should be described by perfect geometric shapes. What is the geometric shape that is perfect? It can be only the circle. How, using circle, can you describe these wandering and bizarre trajectories? And the dilemma was solved by Ptolemaios and the scientists at the time of Ptolemaios, who understood that with combinations of circles, you can do complicated movements. If you want, it was a very ancient precursor of the Fourier analysis from the 19th century. The Fourier analysis tells you that with just cosine and sine functions, which are projections of circular movement, you can decompose, if you superpose them, any signal, any complicated signal. And Ptolemaios set up to have combinations of circles to describe the motion of planets. So maybe there was the main circle, on top of this you put a smaller circle, then another circle, and to describe the movements of the planets, he did something like 40 or something of these combinations, called epicycles. And it was really strong because nobody did better for something like 15 centuries or something like that. They were really, really good, those guys, those ancient Greek scientists. You see, this is a typical example of an epicycle. You have the main circle and the secondary circle, and then you have another one, and in this way, you can reconstruct these Ayring's trajectories. And then Copernicus, in the 16th century, he arrived with a vision which has been considered since now as the emblematic of a revolution in the way we see things. Copernican revolution. Now it's banal. Somebody in politics or whatever has a new idea, says this is Copernican revolution or whatever. But in those days it was really revolutionary. Let's say that we have the sun at the center and see how it changes the point of view. It is an irony because Copernicus himself did not want to be a revolutionary. Actually, he waited for almost 40 years to publish his theory. He didn't want to have any trouble with the church. He himself was in the church. He wanted to be very discreet about this. He published it on the year of his death, and because he really was pushed to publish it by some of his students, saying, go on, publish it, it's a shame, etc., and publicly challenging and so on. So in the theory of Copernicus, what is interesting is that he still needed some epicycles. And a number of them actually, almost as many epicycles as Ptolemy's. And you may argue it was not even a progress, but it was actually, since the time of Ptolemy's, the precision, the accuracy of the observations had increased, and so it was a little bit more demanding to have the trajectories. And so he was led to, even if he could get rid of the big epicycles, he had to add some smaller ones and so on. So it was a big progress, but still quite far from a vision of something stable and simple. And then arrived Galileo. So Galileo took all the big pressure from Copernicus. Copernicus wanted to stay away from the trouble, but Galileo did get into trouble. And in particular because he kind of embodied this tension between the natural observation and the description of the book, of the Bible. Galileo himself believed the two sources should be considered equivalently strong and equivalently important, and you should continuously use both sources to understand the world. And he had these famous sayings. And when Galileo says to understand the world, we have to read from that other book, which is the book of natural phenomena, in which is written in the language of mathematics, of lines and circles and geometrical figures and so on. And that we may say that kind of a big manifesto is like the birth of mathematical physics. And of course it was astronomic observations, the rings of Saturn, etc., etc. And the big storm on Jupiter. And now arrives Kepler. Now, in the history of astronomy, Kepler is a very special moment, a kind of moment of grace in which everything is more simple than it was before, and everything is simpler than it will be later. It's that moment in which things are perfect, beautiful, symmetric, etc. It's also very interesting from the scientific point of view. Euler, so first let's recall the three laws of Kepler, which we learn in high school, and see how simple and beautiful they are. First law, the trajectories of planets are ellipses, and the sun is one of the focal points of the ellipse. So what does it mean? It means, so one way to define ellipse is when you have 2 points, which are your 2 focal points. Then if you take a point on the ellipse, the length to any of these 2 points will vary, but the sum of the length will remain constant. That is an ellipse, and it's very convenient property to draw an ellipse, for instance, in your garden. We call it the gardener's ellipse. You have one peak, another peak, and you take a rope and you go as far as you can after attaching the rope to each of the sticks, and then it draws you the ellipse. So that is the first law. The trajectories of planets are ellipses. It's amazing when you believe it. The ancient Greeks, they knew by heart the ellipses and the conics. They had big theories, treatises about them. And they were obsessed with the problem of the motion of planets. And they never had the idea that the ellipses that they knew so well were the solution to the problems of planets. But it's normal. It's so damn difficult to see those ellipses because we are ourselves on an elliptic trajectory. So if you view an ellipse from something which is moving as an ellipse, of course, it can be any kind of extremely tricky thing. But somehow, being able to see this from a distance and understand that introducing the ellipse will simplify everything was the enormous, fantastic progress by Kepler. Second law of Kepler is about the areas. So the motion of the planet is not constant speed, but there is something which is constant speed, and that is the area which is swept, seen from the sun. Now here is this is a satellite around the Earth, and you see here this is the trajectory. So this satellite will have an elliptic trajectory, and when it's away from the Earth, it's slower than it is. That's the contrary. When it's, you will see the drawing. The area is proportional to the time. So here you will see the two segments in which it will appear. Okay, I put the animation we did was a bit too slow, sorry. I want the area swept, please, go. Yes, here we are. So you see that area here in kind of brown, and this area here in kind of red. The two areas are the same, and in the Kepler laws, it means that it took the same amount of time to do this than to do this. Obviously, then, it was faster here, because that portion was swept in the same amount of time as this one. So when it's close to the Earth, it goes faster, and when it's away from the Earth, it goes slower. And there is something that remains constant speed, that is the area which is swept. Beautiful law. Finding something, again, which is constant speed where it seems not to be. And now is the third law, an algebraic relation between distances and times. For each planet there is a typical time, and that is the time of the year. If the Earth is in 1 year, then Venus has a year which is kind of 0.61, Mars it's 1.9. A year on Mars is about 2 years of the Earth, etc., etc. And when you look at the distances, distance comes something like the mean distance from the planet to the Sun, the demi-grand, the half-large axis actually. Then you will see also that there are these numbers, 0.4, 0.7, 1.5. So for instance, the distance from the Sun to Mars is 1.5 times the distance of the Sun to the Earth. Okay. What can you make sense of this? A priori, you don't see any. And then Kepler understood that if you take the square of the year and divide by the cube of the distance, you have a constant. It will be the same for all the planets. So that is a beautiful, simple relation, cube, squares, very, very neat. And if you take these here and you square the numbers on the left and you cube the numbers on the right, you will obtain 1. For instance, for Neptune, the year is like 164 years. 1 year of Neptune is 164 years of the Earth. You take the square and divide by the cube of 30, which is like the distance from the Sun to Neptune. You find 0.99, which is almost 1. So that is the third law of Kepler. Beautiful, you have these three laws, and it's an example of extraordinary science. One first remarkable thing is that Kepler obtained these three laws just empirically, by working out and trying all kinds of relation. It was a really empiric discovery without any model for it. And the second remarkable thing is that Kepler was a kind of weird scientist. If you read Kepler in the text, you will find a mixture of science and mystical considerations and so on. Voltaire, who was passionate with the history of sciences, makes fun of, not fun, but he says it's amazing that Kepler has this weird saying. So he says, Kepler says that the sun has a soul, not an intelligent soul, but a vegetative soul, an acting soul, and that the sun turning on to himself attracts to him the planets, but the planets make a revolution on their axis, sometimes presenting the sun their friendly side, sometimes presenting the sun their enemy side. And the enemy side is repulsed, which induces the course of the planets. And Voltaire comments, he says, to the humiliation of philosophy, it is from this very little philosophical reasoning that Kepler concluded that the sun had to turn around its axis. Mistake led him by chance to the truth. That is something that we know well in science, actually. Sometimes you have good ideas for bad reasons. It occurred to me several times in my career. And sometimes somebody gives you a hint that is totally stupid, but actually gives to the right discovery. You should never neglect or get rid of the ideas. And Kepler, even though his arguments were really impossible to understand and very bizarre, he was led to the truth by this. There are other famous examples of this kind. And by the way, Kepler made history with his three laws for describing the motion, but he did not stay in history for other of his contributions. For instance, he tried to explain the distances between the Sun and the planets by putting the 5 planets in correspondence to the 5 regular solids, the 5 Platonician solids, the regular ones, like the cube and the dodecahedron and so on. There were 5 of them, 5 of these, so he thought there had to be a correspondence and tried to build this kind of model to explain it. And of course, you see, this makes no sense. Why on earth would there be a relation? But in the eyes of Kepler, there had to be a relation. And it's important we retain this also. Motivations that lead the scientists in their discoveries may be very irrational, but after all, that's life. We human beings are made of rationality and irrationality that is mixed, and very often irrationality is important to get some good conclusion, even when it's about getting some good rational conclusions. Now arrived Newton. With Newton, we change era. And in particular with the book of Newton. You know, Newton has this amazing book, Philosophiae Naturalis Principia Mathematica, which was the first account to put on totally mathematical basis the motions of the planets and the sun, starting from very fundamental laws and geometric problems and solving differential equations. And in particular, this law of universal gravitation. In France, Newton was translated and actually improved by the great French mathematician Émilie du Châtelet, who remains as one of the few of those heroic female mathematicians in those days in which women could not access university, could not enter Academy of Science, were barred from any circle of discussion, etc. And she at the time was probably the best specialist of Newton in the world. And the great genius of the law of Newton is the following: universal law of gravity. Now, let me tell you right from the beginning, Newton is not the first one to have imagined this law. In the time, there were a number of scientists. There was Hooke, there was Barrow, there was Lorentz, working on this idea of a force between the planets to explain the motion, a force between planet and the sun. But what really makes the difference between Newton and the other ones is the book. The fact that he has this book in which all the things are expressed and explained in such a beautiful and synthetic manner, which made the book the lasting reference for the 100 years to come. And this was a new era. What does universal gravitation say? So first, in general, if you have a system and there is a position, let's say it is x, so the acceleration of the system, x double dot is the acceleration, is the force divided by the mass of this object, of this system. This is the fundamental law of physics, of mechanics, as we call it in high school. And in this case, the force, the intensity of the force is proportional, so G is the proportionality constant, to the product of the two masses divided by the square of the distance. If you have the idea that there is a force, and if you know the Kepler laws, actually it's easy to find this square. It's the only law that is compatible with the 3 Kepler laws. But the big fundamental step is to assume that there is such a universal law. Now, the important thing here is universal too. In the time of the Greeks, they would say there is the planets and the stars. Or later, Kepler would say there is the sun and the planets. But Newton tells you, we don't care if it's sun or planet or you and me or satellite or whatever. The only thing that matters is that it has a mass. Whatever has a mass attracts whatever has a mass. This is universal. And with this just one law, he's able to recover the 3 laws of Kepler. Because if you solve this for just 2 objects, then you will recover the ellipses and the laws of the eras and the law of the cubes of the distances and square of the time, etc. So, at the same time, you simplify it even further, just one law, and that is your fundamental equation. But at the same time, you introduce the enormous problem, the stability problem, which would remain in the hundreds of years to come as the archetype of a big fundamental problem in mathematical physics, attracting new material and inventivity of mathematicians. What is the problem of stability? Because as soon as you say it is universal, then okay, if I look at the forces which are exerted on the Earth, there is not just the force from the Sun, which gives you elliptic trajectories, but also the force by Jupiter, and the force by Mars, and the force by the Moon. And it becomes a complicated equation with not just two bodies, but many bodies. So if you are solving for one sun and say 9 planets, when I was young, I was told that there were 9 planets. Since then, astronomers decided Pluto was not a planet any longer, etc., but a small planet, whatever. Maybe 8, maybe 9, maybe 10, maybe 15 if you have a few satellites. But if you look at all the interactions between them, these equations are much more complicated. Certainly, this will not be ellipses. It will be approximate ellipses only. Who knows if they will be closed? They, in general, will not be closed trajectories. What do we know about their stability? And then Newton was like this. Who tells us that this system will remain how we know it for, let's say, thousands of years to come? And he had a big reason to be anxious about this. So first, let me tell you, if you have just one interaction and many bodies, things can be very, very complex. In the animation plays, you see an example of an n-body problem. N is the number of stars, let's say, which are in attraction. Don't care about the music. Look at this kind of complicated patterns. This is what occurs actually when two galaxies collide. And you see this and you have to describe this mathematically. It's even not clear what kind of question you'd like to ask. Okay, this was an astronomer who liked to make these videos and put music on them. And you know what is the equation behind the movies that I showed you? A Newton equation, that's all. Just a single Newton equation, just one force, which is any two bodies attract each other with the reciprocal of the distance. See how complicated it is. So it's not, even if the law is simple, the effects can be extremely complicated. After you've seen this, then who tells you that the trajectories of the solar system are stable? However, in the solar system, there is one element which is important, is that the sun is really bigger than all the rest. This is all the planets, this is the sun at real scale. This is the Earth compared to the sun. Now, if you take the masses, all these masses together, and you add them, you get about 1/1000th of the mass of the sun. So, the solar system really is a perturbation, as we call it, of the sun. A small variation of just the sun. And so, you enter this problem. If we perturb a little bit the equation that you would have, if it was only the attraction of the sun, does it remain stable? And Newton understood the problem, said it clearly, but was unable to solve it, and was very embarrassed. I told you 1/1000th. Now, and here is the mathematical way to write the problem. So this is like the oldest of the problems of mathematical physics. You give yourself the masses of the sun and the planets, and the positions, and you write the differential equation, which is Newton 1, and you ask, over the long time, how will be the trajectories, x1, etc., xn of t. Now, if you have a perturbation, so in your force there is a small effect, which is of relative order epsilon, and epsilon is about 1,000th, you would expect that there is a significant effect after how long? Answer is easy, 1 over epsilon. If your bank account loses 1% or varies by 1% every day, then after 100 days you may be in very bad shape. This is easy to understand. It's the same as the scale of the sun. If there is a perturbation of order 1 per thousand, then after 1,000 years, you expect there will be a big effect. That is a problem. We know from the ancient records of astronomers from Babylonian and others that 1,000 years ago, 2,000 years ago, the planets were about the same position as nowadays. No significant variation. How come then, if the perturbation is of the order 1 over 1,000, that we don't see those variations after 1,000 years? Newton had no clue, and the way he treats it is very bizarre. As if he suggests that maybe God Almighty resets things in a stable way when it goes out of control, so maybe every 1,000 years or so, who knows. And then there was big dispute between Leibniz and Newton anyway. Leibniz liked to ridicule Newton for thinking that God needs to intervene on the real world, while Leibniz thought God gave the laws of physics and then let it be, and so on. It took 100 years before the controversy could be really solved. And this was solved by means of the French astronomers of the end of the 18th century, Laplace and Lagrange. The legend, there are always legends, say that when Laplace gave to his emperor Napoleon his treaty of mechanics with all the trajectories, and Napoleon asks, where is God in all that? And Laplace answers, I didn't need to use it. And so he could go on, and just the equations are enough to get the stability. So what did they prove? Actually, it was combined efforts of Lagrange and Laplace and building on the work of Gauss. And they found that the stability of the distances between the sun and the planets is of the order of 1 over epsilon squared. At least if there are no resonances. We'll come to this in a second. But 1 over epsilon squared is remarkable. 1 over epsilon squared is of the order of the million years. And it's amazing to realize that at the end of the 18th century, mathematicians were able to predict, studying the equations with mathematical tools, with subtle mathematical tools, that the positions of the planets would remain stable for about 1 million years, which is way larger than the scale of any human records. This was absolutely remarkable. Now, we know now, and I will come back to that later, that the time for which we know for sure that there is stability is not larger than something like 60 million years. So we are not far here from the optimality in the sense of the order of magnitude of the stability. What is the resonance and what could go wrong? How could instability occur? Let me try to explain it. Imagine that this is out of scale, but imagine that here we have the sun, here we have a small planet, and here we have a large planet. Maybe this is Jupiter, this is the sun in big, and this is the Earth around the sun. Of course, it's not out of scale. And now let's say we want to see if Jupiter has significant influence on the trajectory of the Earth. Sometimes Jupiter is behind the sun, which has an influence of slightly making the Earth going closer to the sun, slightly closer. But sometimes Jupiter is on the other side of the sun, which has the effect of making the Earth slightly farther away from the sun. So perturbation is sometimes slightly closer, sometimes slightly further away. What will win? Okay. Now imagine that there is no correlation, as we would say, between the position of the Earth and the position of Jupiter. Then this means that anyway, there should be some cancellation because it will be sometimes less, sometimes more, in a kind of random way. And if there is no kind of regularity, if it's very irregular, chaotic, statistic, whatever, it should compensate each other. As many times closer and as many times further away should compensate on average. What could go wrong? When could it go wrong? It could go wrong if there is a resonance. Now let me explain what is resonance and let me explain why it can be unstable. Let's again assume we have a sun and just two planets. And we want to understand the trajectories of these two planets. And assume that there is the year of planet 1, let's call it T1, the year of planet 2, let's call it T2. Let's write alpha as the ratio between these 2 years. And assume that that number is a rational number, that is P over Q, where P and Q are integers. Then what does it mean? It means that every time that one of the planets orbitates P times around the Sun, the other planet will orbitate Q times around the Sun. So they will be in exactly the same position. After these P years of planet 1, they will be in exactly the same position as before. So if over that period of time there is a certain variation like this, then over the next period of time it will be the same variation, and then again and again and again. And so it will build constructively and make it depart in a way that will be linearly proportional to the amount of time. And so there will be instability in a time that is of the order of P times T1 times divided by epsilon. And if there is no such number, Q over Q, then there is stability for any time which is smaller than 1 over epsilon squared. So can you see here how mathematics enter the problem in an unexpected way? To know whether a number is rational or irrational is a question that seems just like a mathematician's problem, not a physicist. Who cares about whether a number is rational or irrational? Actually, rational numbers are accidents in the eyes of mathematicians, but any number is kind of rational in the eyes of an experimentalist. It was a big surprise when it was discovered that irrational numbers existed. The square root of 2 is irrational, etc. And it was at first, when the Pythagoreans discovered the irrationality of square root of 2, they were shocked. There were even legends about something that some people were killed for not preventing them to declare and state that inconvenient truth. Rationality was seen as something harmonious. Irrationality was something pathological. And now there is this irony. We discover that irrationality gives stability in this problem. Rationality gives instability. And you see how a problem related to numbers and approximation goes into a problem of solution of mathematical physics. Now, by the way, there is an example of something that is near resonance in the solar system. When you look at the year of Saturn divided by the year of Jupiter, it is close to 5 over 2, which is so close to be a rational number with a small p and q. And that explains why the motion of Jupiter over several hundreds of years is stable in one direction and then stable over several hundred of years in another direction. It's because it's near resonance, you have this large-scale motion over hundreds of years, not more, but over hundreds of years. Now, this gave, so at the end of the 18th century, this idea, if we are in the generic situation that is irrationality, then you have stability for thousands of years. And for a long time, it was kind of the best you could achieve. And at this time, end of 18th century, the whole of astronomical observations could be explained with just the law of Newton. Now, 1 century again later, mathematicians came with new questions, and in particular, the best mathematician of his time and the last universal mathematician, as we say, Henri Poincaré. Henri Poincaré not only understood and worked in all branches of mathematics of his time, but also understood and taught at university all branches of physics in his time. And he worked on this problem asking a question, okay, over 1 million years we have the stability. Now, what about 1 billion years? If we want to solve this equation for very, very large time, will it still remain stable? And he discovered that those problems are actually extraordinarily complicated, and that was the birth of modern theory of dynamical systems. In fact, the story has a kind of very dramatic turn for Poincaré. He was participant in a very broad and famous competition instigated by the King of Sweden for mathematicians worldwide, and he won the competition for a big manuscript proving with a number of new tools that a baby model of the solar system would be stable for all times. And he wins the prize and he gets the fame. There was a big amount of money with this, etc. And the manuscript is sent in the main journal of the time, Acta Mathematica, all around the world. And then, after it is sent and awarded, etc., Poincaré discovers that there is an enormous mistake in the papers. Enormous mistake, which actually was pointed out by the referee, but he had not taken seriously this thing. And then he discovers it's all completely wrong. And the most amazing thing is he was able to repair the mistake in spite of the pressure, rebuild the whole, with just one difference is that now his new conclusion was the opposite of the initial one, that it had to be unstable rather than stable. Mittag-Leffler, who was the editor, managed to retrieve all the copies of the journal that he had sent around the world. He destroyed them all except for 2 copies, which are still kept as testimony in Mittag-Leffler Institute near Stockholm. And Poincaré paid for all the expenses, actually, so all the money he had got from the prize was spent by destroying the traces of that failed paper. And the new tools are amazing because it's all a new theory. And in germ, the theory of chaos, in which Poincaré shows the notion of unpredictability. If you make a very, very tiny change in the initial conditions, super tiny, it may be that the conclusion in the long run will be extraordinarily different. This we call the sensitivity to initial conditions. Poincaré also understands that if the system is mixing enough, then it may be statistically stable, even though it's impossible to predict in which precise state we are. So that you would say that, for instance, the system has 10% chance of being unstable and 90% chance of being stable, things like this. These have been the 2 driving principles of theory of chaotic systems ever since. And you see here how also the fact that thinking of these astronomical questions gave rise to tools which were useful for many questions. Actually, many of the tools of modern mathematics started with issues related to stability and related to astronomy. For instance, we all know and use matrices from early age. Matrices were developed by Lagrange and Laplace to solve the differential equations of Newton in their linearized version and understand about the stability and so on. Now, after Poincaré, go again about 60 years later, 70 years later, and then the problem is revisited by Kolmogorov and his disciples, in particular Arnold, in particular Moser, and perturbative theory, asking the question, okay, Poincaré showed that there is a possibility of instability, but let's see if it's likely to be stable. And this was a complete blow, and he managed to prove that if the planets are very, very tiny, in an ideal world, the planets would be very, very tiny compared to the sun, extremely tiny, then with probability 99%, the system would remain stable. And even if there is no law constraining the planets to be stable, they would do so. It was combining probability theory, measure theory, and equations of mechanics. It was brilliant. The story has it that after the death of Stalin in 1953, Kolmogorov was so full of joy and wanted to share his joy with the whole world that he thought, I will prove a theorem that is impossible and unbelievable. And I will find some freedom in a theorem in which things seem to be not free and unstable. And it was impossible and surprising. I discussed with some older astronomers, and they said, yes, when these mathematical papers arose, and they were published, these papers by Arnold about why solar system would remain stable very likely, it was a complete blow in the astronomer world. And you say, how these guys from mathematics, what new idea did they have that changed the situation? It is interesting, because actually, when you try to apply the theorem of Kolmogorov directly to the solar system, it's impossible. Okay, first because it was an idealized mathematics problem, idealized mechanical problem, which has less degeneracy than the solar system. This issue was solved completely only 50 years later. But also because epsilon here has to be ridiculously small, not 1/1000, but 1/1 billion of billions, something like this. So the theorem does not really apply to the real world. Even if it does not apply to the real world, it was considered and is still considered by astronomers as a legitimate inspiration about the real world. Very often in mathematical physics, the world and life is so complicated that it's just doomed to try and apply directly the mathematical theorem to real life. But still, you can hope to find in the mathematical world some inspiration to understand what is the physics world like and to understand where to find the new source, for instance, of stability. And this was a thing Kolmogorov introduced a new property and a new actor in the game known as the Diophantine property. What is Diophantine? Diophantine number is refinement of this idea of irrational number. We know what is an irrational number. An irrational number is a number which is not in the form of a fraction, p over q. Any number can be approximated by a rational number. For instance, square root of 2 is not a rational number, but square root of 2 is approximately 1.414,213 or something like this. And we can approximate square root of 2 by rational number at any accuracy we wish. Even the antique Babylonians, they would approximate square root of 2 with such precision. But it may be hard or it may be easy to approximate irrational numbers by rational numbers. And Diophantine number is a number which is difficult to approximate by fractions. Not only it is not a fraction, but it's difficult to approximate by a fraction. In which sense? Whenever you try to approximate alpha by p over q, when p and q are rationals, the error has to be at least like an inverse power of the denominator q, with a constant c and a constant r which are fixed. When you have a number like this, you call it Diophantine. Depending on c and r, it may be more Diophantine. If r is small, then it will be very Diophantine. If r is equal to 2, which is small, you have a number which is strongly Diophantine. If r is equal to 100, it will be less Diophantine. But what Kolmogorov discovers is that the more alpha is Diophantine, the more the configuration is stable. Now here we have another twist. Let's give examples of Diophantine number. Actually, the number and the interval 0, 1, for instance, which is the most difficult to approximate by fractions, is not an extravagant number. It's not a very bizarre number. It's a very famous number. It's just the good old golden ratio, which is square root plus 1 over 2, or if you use square root minus 1 over 2. That ratio is very difficult to approximate, actually, when you try to write it in a continuous fraction it's 1 plus 1 over 1 plus 1 over 1 plus 1 over, etc. And the fact that you have only 1 here is the thing making it very difficult to approximate by rational numbers. So you can take R equal 2 for the golden ratio and see something like 0.3. Now here is the other irony. Moments ago we discovered that irrational eventually is associated with stability, contrary to what was coming from the ancient Greek. But on the other hand, we know that golden ratio was praised as being something associated to harmony. And even at some time in the 19th century, people became crazy about golden ratio and started to find golden ratio in nature everywhere. And usually mathematicians don't like so much to talk about golden ratio because they believe it is overrated and that there is too much fuss about golden ratio. But here is an example in which golden ratio really is there. If you ask which is the most stable configuration to put 2 planets in orbit around the Sun, and the answer is exactly if the ratio of the years of the 2 planets is equal to the golden ratio, this is the most stable situation that you can hope for. Wow! Can you imagine these issues about approximating numbers? You end up seeing it appear again in the good old problem of stability of solar system. So this was a blow. And then the people, they saw this and they say, wow, this theory by Kolmogorov is so beautiful that it has to be true. Often in mathematics it's like this. It guided me at several occasions, occurrences in my career. You find the relation, say this thing is too beautiful, some conjecture. It's so beautiful that it has to be true. Sometimes it's true, sometimes it's a trap. And in this case, it was kind of a trap. After the 50s and the theory was published, all the specialists of solar system, they said, oh, eventually, it must be stable. With Poincaré, he thought it was unstable. With Kolmogorov, intuition is so good, it has to be stable. And this remained true until the 80s. And in the 80s came a new era again. This was a time at which the power of computers was becoming strong enough to solve the equations of the solar systems over very long periods of time. 2 people in particular were working on this independently. Jacques Lascar in France and Scott Tremaine in Canada. And they, with different techniques and different algorithms, they put this on computers and tried to see on the very long run, do we see stability or non-stability? And this was real art to find a good numerical method so that it can resist the errors, etc., etc. Lascar, on his computer, he solved the kind of simplified equations of evolution of the orbits in which it was 150,000 terms of degree 5, polynomial degree 5, in the differential equations with 16 real variables solved at the same time. Can you imagine the craziness? That is the equation. They solved these equations, and the results which they obtained were exactly the same, coming from 2 different approaches, which gave very strong confidence in the result. And the conclusions was, in the end, unstable, my friend. Or at least on a significant proportion of the trials, it was unstable. And they found that in about 10 million years, the uncertainty on the positions of the small planets becomes 10 times as large. It's an accident that it fits so nicely with 10. So, if you think about just 10 million years, it's not a problem. It means if you have an uncertainty of, I don't know, 1 meter, then it will be an uncertainty after 10 million years. The uncertainty will be of 10 meters. Who cares? But now, if you look at over a period of time of 100 millions of years, so it's 10 plus 10 plus 10. So it means that it will be multiplication by 10 times. So 10 to the 10. So it's not just 10 meters, it's 10 billions of years. So 10 millions of kilometers, and then you have a big possibility of discrepancy. Here is one of the typical simulations of Lascar. So Lascar runs and works on the evolutions of the orbits. Like, let's see how the evolution of the orbits are. These are the orbits of Mercury, Venus, the Earth in blue, Mars, Jupiter, Saturn, Uranus, Pluto, and this is the time in thousands of years. And you see, over typical times of 100,000 millions of years, not much. But sometimes in simulations, you end up in seeing catastrophes. And the numerics predict you that sometimes you will enter into this, which means that there are collisions when the orbits cross, resulting in disastrous events. So sometimes there are futures in which there is, for instance, collision of the Earth with Venus. And they can see, because you see, if you run this 1,000 times and you have 10 times the collision, it means that about 1% chance of collision. Actually, what they show this is exactly this. It's possibly stable, likely to be stable, but in practice, there is a significant probability, meaning something like 2 or 3%, which is non-zero, 2 or 3% is not so negligible, that there is a catastrophic event like a collision between two planets in our solar system on the time scale of hundreds of millions of years. And Lascar shows that you cannot make prediction over the positions after more than 60 million years, which is not much. You know, 65 million years is the time when there was the asteroid colliding planet and the extinction of dinosaurs, etc. It's very small compared to the age of the Earth. Lascar is convinced that our solar system used to have more planets than it has now. That a few billion years ago there was more planets which disappeared, which were ejected from solar system. So it's impressive to see these things. And Jacques Lascar even discovered that when you want to take into account the equations, the number one source of instability to predict the positions is not Jupiter. These are two asteroids, Ceres and Vesta, somewhere between Mars and Jupiter, very, very small. Their mass is something like less than 1 million, it's like about 1 billion of the mass of the Sun. It's ridiculously small. Ceres is called a small planet, but Vesta is not even called a small planet. It's an asteroid. But they are in resonance, so they have effects which can accumulate and this propagate throughout the solar system. It's amazing. Nobody had expected this 100 years ago, that you would have to take the trajectories of Ceres and Vesta in account to get these predictions. This is recent research. It's a few years ago by Lascar. You see, it's 15 years ago, which shows you that even in this problem, which was set by Newton in the middle of the 17th century, 15 years ago, there were still some new and striking discoveries. Mathematical physics, even in classical physics, has a number of surprises and constant go between the mathematics and the physics, and subtle mathematics coming in the way to explain some new physical phenomena. Now, see that solar system led to scientific progress, and from there emerged like modern mechanics, perturbation theory, chaos theory, ergodic theory, Kolmogorov theory, etc. And a lot of understanding in the measurement of time and space. So the mere fact of asking the question and the fact that it became a reference problem to develop methods and tools was very important. Now, what about a galaxy? In the solar system, maybe 9 planets, 1 sun, and already is so monstrally difficult and hundreds of years of surprises. Now, in a galaxy, you may have hundreds of billions of galaxies, of stars in the galaxy. What do you do with it? Again, it was a problem which led to a lot of progress, and even though we may think it's just a more complicated version of the stability of the solar system, actually it goes into completely different areas of mathematics. In particular, the statistical treatment, according to the theories initiated by Maxwell and Boltzmann at the end of 19th century to understand the gas as a crowd of particles that you describe statistically. It was James Jeans, British astronomer, at the end of at the very beginning of the 20th century, who suggested to apply the theory of gases and plasmas to galaxies. Not because they are made of plasmas, but because a star in a galaxy is a bit like an atom, like a molecule in a gas. You can describe the whole thing in a statistical way and ask questions about, is it in thermodynamical equilibrium? Is there some statistical collisions? Are there some collective effects and so on, which were very familiar in the development of thermodynamics as a statistical field in the 19th century. Which should be the big model? There are two big models that are two reference differential equations that are studied in the field of statistical physics, and this is the field in which I did my PhD and a lot of my research work. And on the left, it's called the Boltzmann equation. On the right, it's called the Vlasov equation. If you wish, the one upstairs, take it as a poetic character if you don't know this notation. It's common to both equations, but the sequel is either the Boltzmann for gas or the Vlasov for plasma. And actually, you mentioned my 2010 Fields Medal. It was attributed for research which was bearing some of it for the Boltzmann equation and some of it for the Vlasov equation. One of the main discoveries of Boltzmann was if you put this quantity called S in the equation, if you have collisions, it will systematically increase, and that is the law of increase of disorder from thermodynamics. And if you consider the Vlasov collisionless equation, it will remain constant, and that is the fate of collisionless plasmas or galaxies. And galaxies are typically collisionless, so for galaxies, it's rather more like the equation on the right than the equation on the left. It will be much more like this. And the stability in the eyes of Boltzmann was related to the collisions. So with the eyes of Boltzmann, we would believe that galaxies are typically not stable. However, in the 60s, British astronomer Lyndon Bell said that actually when we observe galaxies over a very long period of time, not so long period of time, they appear to be stable. And this cannot be explained by the collisions, so it has to be that there is another source of stability, not due to collisions, not due to entropy. Now, we know that astronomy is a very creative field, and sometimes scientists like to make jokes about astronomers being very prone to imagine new kind of objects, new kind of physics, new black matter, new whatever. Lev Landau liked to joke about astronomers saying that they are very often erring but never in doubt, and always going there with good conviction to this. And Lyndon Bell suggested that this phenomenon would be what he called violent relaxation. Violent relaxation already in itself, the wording is very strange. How can you be relaxing and at the same time in a violent way? And then he suggested that this would have to do with a phenomenon that physicists discovered in the 40s with the work of Lev Landau, which was named the Landau damping. So Landau damping is a property according to which a plasma would be stable even in the absence of collisions, due to effects which are not related to collisions of disorder. It was a shock when Landau proposed this. It was in a paper in the 40s in which he was very violent in his wording, Landau. And in the paper, he says things like, this and that person have worked on the equations of plasmas, and almost all their results are wrong, and now we'll explain, etc. And he goes on, and he shows that if you take the equation of plasma, linearize it, so replace it by a simpler version, linearize near an equilibrium that is stable and homogeneous. Then you go to an equation that you can exactly solve, which has built in a stability mechanism. And this was called the Landau damping. It was extremely important. It was observed after it was predicted by Landau, and it was extremely important in practical experimental work on plasmas later. Plasmas are around in all kinds of phenomena. It can be in matter and the presence of shock. When the electric shock will dissociate the atoms in the air, the molecules in the air, they will constitute plasmas, etc. Every time you are able to take the electrons away from the nuclei, you construct a plasma. Now, this was another stability problem and came a controversy also. And if you wish, this would be the stability problem of the plasmas, as was stated implicitly by Landau. Let's show that if you take the plasma equation, which is the statistical version of the Newton equation, it is stable. And what Landau showed is that for the linear equation, you have close to equilibrium the stability. But now, what tells us, who tells us that if it's true for the simplified equation, it will be true for the big complete equation, the nonlinear equation as we say. And then this was a controversy. What you prove for the linear equation, this one is upstairs is linear, this one is nonlinear. Is it true also? Why nonlinear? Because upstairs you know that h in each term of the equation appears only one, while on the second equation you have h and h in the same term which appear, so it's a quadratic equation actually. It was my enormous luck, one of my enormous lucks, that I came around this problem and became interested in this problem at some point. It was an accident in some sense. I was working with my collaborator and former student Clément Mouot on a different problem. And one day we had this work session. Let's work on the stability for Boltzmann equation, which is a different equation. Let's try this and try that and this. And we made some try of computation on this and that. And then we tried to understand. And then Clément had something, and he said, like, but this reminds me of a conversation I had 2 years ago with our colleague in American University about Landau damping, so maybe it can help. Now, if I tell you very frankly, if at that moment on our work session, Clément had not had this reminiscence about that guy 2 years ago we had discussion with, I would not have worked on this. I would not have got the Fields Medal. The rest of my career would have been different. Our careers in mathematics or in research in general, they can be very fragile. They rest on very, very tiny coincidence. And there was another thing in the same discussion in which I remembered another discussion that I had with another colleague 3 years ago, and which also led us to somewhere. So these discussions here and there, at years of distance, they can make a crucial difference. And then we started working on this, and at the beginning we did not even know what we wanted to prove. It took us, on the whole, 3 years and a half to solve the problem. That is, to really have a theorem that tells you if it's linearly stable, then it will be nonlinear stable under this and that condition, under simplified conditions here and there, but completely solving this in mathematical way. But it's not just solving the equation, the problem. It's also finding new tools and intuition, including relations between these physical problems which the physics community had not seen. For instance, we found that there is a deep link between 3 paradoxical phenomena. One is this nonlinear Landau damping stability even without the collisions, and one is the theory of Kolmogorov, stability under small perturbation, even if it's not compelled to be stable. And one is something called ecoplasma, which physicists have known as a kind of consequence of the, as related to the Landau dumping. Experiment of Malmberg, Wharton, Gould and O'Neill, end of the 60s, the experiment goes like this. You prepare your plasma in the lab at equilibrium, statistical equilibrium, and there is no electric field in your plasma. Plasma, think of it as a soup of electrons and nuclei. And the electrons are the very rapid guys that determine the electric field. And at a certain moment, you send an electric impulse in the plasma. And then, of course, because you send an electric impulse, there is an electric field. And it will typically oscillate and then decrease. And it will be calm again with no electric field. Then after some small amount of time, you send another electric pulse on a different frequency. And then it will rest. And then you do nothing, and you will see spontaneously at another frequency a wave emerge that you have not seen. It's called the ecoplasma. To give an image, imagine it's us as if, I don't know, imagine there is this robbery and there is a burglar coming in the house, and the burglar flies away because there is a dog chasing the burglar, and you see the burglar going out, shouting, the dog going out, shouting whatever, then it's like calm. But in the distance, you hear after a big shout telling you that the dog has caught the burglar. Here it's a bit like this. It's like one wave has managed to catch up the first wave in a realm of very high frequencies within the plasma. Oh, anyhow, we found that these three phenomena are intimately connected, and we found it in the analysis of the problem. And we found that there is a very subtle effect related to resonances which had not been discovered or uncovered by the physics community, and in which the key thing was not about whether a number is Diophantine or not, but about the regularity of the perturbation. Mathematicians say regularity about a function to see whether it varies widely or smoothly. And the right amount of regularity in this was a very specific class of regularity, which most mathematicians actually never use, called the Gevrey regularity, which is intermediate because infinitely differentiable and analytic regularity. And we discovered it is the key regularity for this problem. This was our paper. As I told you, 3.5 years of my mathematical life. It's just one proof, basically. Almost 200 pages. It may seem as something daunting when you're working in high school and proofs are a few lines or maybe a couple of pages long. But I tell you, it's just work and being familiar with the problems. And the whole of my career, between the time I learned in medium high school what is a proof to this thing, was gradually learn to make proofs that are more and more complicated. And when you are in it, you manage to see becoming an artist about proofs, blocks of proofs, resonance between proofs, changing the tools, etc., like an architect. These 3 years were like the pregnancy, and the publication of the paper was like the birth of the article. After the birth, there is the life. What is the life of a mathematical article? Well, lots of adventures. The paper will be used by other people. Some people will prove it again. And I tell you, when it was first reproved by other mathematicians using slightly different tools and in a more concise proof, I was not jealous of them having a new proof. I was relieved, thinking, okay, if now they managed to prove it in different way and get the very same conclusion, then it was true. Because otherwise, you always have this slight doubt, who knows if there is a mistake that was hidden. After all, if Poincaré did huge mistake in his paper, anybody can do huge mistake in his papers. But then, after these guys, they reproved it, then they adapted to a new system using this tool. Nader Masmoudi and Jacob Bedrosian were able to solve a very old stability problem arising in fluid mechanics, which had been stated 100 years ago by specialists of physics about stability of some equilibria in fluid physics near the boundary. Other people adapted it to systems in the whole space. And now it's dozens and dozens of papers who have taken the material, refined it, treated variants, etc. So that's the life of the paper, in which it had been turned into a theory and several branches and so on, and arrived at the stage in which even me and Clément, who initiated this field, are unable to follow all the developments. It's always like this. A good theory in science always overcomes the person who initiated it. And that is also an example of how new developments can go in the research, and be part of this enormous, very lively movement that is the mathematical physics. Let me end up concluding that even at that level of refinement, usually in mathematical physics, we only consider droplets in the ocean of the problems. Newton himself, he said, very famous book, he said, I was like a kid on the sand beach playing with pebbles, and I found a few pebbles which are more shining than the others, saying that this is just a few shiny things in front of the whole world. But this is really like this. Even with those theories, we understand just a tiny bit of the reality. Imagine this, that after hundreds of years, just for the old solar system, we have such rich theories and such partial conclusions. When I was a student, one of my professors, Ivar Ekland, very famous specialist of dynamical systems, did important work in mathematical economy and so on. I remember him telling us, and it was in the middle of the 90s, he was telling us, we don't know if solar system is stable, which was such a strong statement to say. Now, 30 years later, we can say, we know that we can't know if the solar system is stable. You see all that enormous ingenuity to arrive at such a poor conclusion in a way. We know that we can't know if the solar system is stable. But we know that the solar system is likely to be stable, but that there is a non-negligible probability that it is unstable. All these enormous treasures of cleverness to arrive at such partial conclusions. It's the general life, mathematical physics, because the reality is that the world is so amazingly complex that we can only grasp a tiny fraction of the reality. But let me say that this makes those tiny fractions even more precious. When you find one of these papers and find the connections, it's really a treasure for you, for the mathematical community, for the physicists, for the whole world after all. Thank you for your attention.
Thank you, Cédric, for this beautiful journey in stability throughout the ages. Any questions, comments? Yeah.
So I have a Diophantine question. Because you explained these Diophantine numbers, which are difficult to approximate by rational numbers. There is this Dirichlet lemma where you can take R to be 2 and C 1. So basically, are the most complicated numbers to approximate those where C is probably big, but R is somewhere between 1 and 2?
What is important for you is not so much in the proofs, is not so much the precise value of C, is the fact that you can take the power R that is bigger, that is strictly bigger than 1, and the fact that you will then increase the constant C in the number so as to take eventually the enormous proportion, the outmost proportion of numbers. The important thing about Diophantine numbers is that they make up a set of full measure, and by making the constant and the exponent vary, you get the whole of them. But for any constant C and constant R, you will get some kind of layer of stability. And if you increase and increase, you will make your phase space increase with more and more stable. And to make it increase, corresponding to increase and increase, corresponds to making the perturbation epsilon smaller and smaller. I don't know if you will have to explain it, you would have to write the formulas in there, here and there. But eventually, it's a measure theory lemma in which you will get the more and more numbers by increasing the C and make it a converging sum.
Okay, other questions?
Yes, can you explain what is the damping exactly?
What the damping?
Yeah, for the linearized equation.
Yes.
Already.
So consider, let's say you have this linearized equation in which the unknown is the perturbation, the size of the perturbation. So let's say you have statistical equilibrium and you put a tiny variation and you look at the equation for this tiny variation. So you solve this equation and the damping phenomenon tells you that if you solve the equation, it will, in large time, go to zero, either in positive times or in negative times. Does not matter. That is called the damping. And it's called damping because it means typically that if you agitate your plasma, so send a small electric shock, then spontaneously it will go back to zero electric field, even in the absence of collisions. Why that is surprising? Because in general, relaxation phenomena involve some kind of irreversibility. For instance, most of a large number of stability around us is related to friction. Friction is the thing that makes us, being able to walk without gliding. If there was no friction, the whole world would be very chaotic and unstable. And friction is a dissipative mechanism in which entropy increases and you have some typically heat is produced at the level of friction, etc. So the big thing that we learned from the 19th century physics, statistical physics, is that irreversibility is associated with damping, reduces the amount. Just like, friction takes out some of the energy of the mechanical system. But in the Landau setting, in the Brazil setting, there is conservation of energy, conservation of entropy. The system really looks like conservative. So you would think that it will preserve, the perturbation will be preserved. But it is not, it is damped. This is possible only because it is in infinite dimension. Infinite dimension would be impossible. But the fact that there is infinitely many degrees of freedom makes it possible to kind of send the perturbation to infinity. So that in theory, it is still there, the perturbation, but in practice, it considers an agitation, oscillations which are so high that you lose sight of them. You cannot see them. Like when you have an electric signal which oscillates very, very fast, if you try to measure it, you may see some flat signal because the variations are too fast for the measurement operator. Somehow it's this kind of phenomenon that there is at work in the damping. So the Landau damping is relaxation through, if you wish, oscillations becoming very, very fast in a confined way. And what we discover is that there is, at the top of this, the ingredient of the regularity, which has to be very finely calibrated for it to be robust.
Okay. Is there a critical quantity that controls this, like an entropy or an energy?
There is a kind of norm which allows you to get and see how things work. It took us quite some work to find the norms, and actually we went to crazy amounts of complexity in the norms in first version of our work. We simplified it later, but it's kind of and critical is kind of you kind of find how to make a focus on the higher and higher frequencies in such a way that damping would correspond to the preservation in another norm which focuses more and more on high frequencies. So at some point, we changed the stability problem into a problem of existence of a reasonable solution to the whole equation, but we called it gliding norm, a norm which kind of focuses automatically on those frequencies and which changes with time. So it was one of the key tricks there. There is a critical exponent related to the regularity, controlling if the perturbation is smooth enough or not. And we did not prove the critical regularity, but we made a guess and explained why the guess would be true. Later was proven that it was indeed the critical regularity for this.
I have a last question.
Yes.
Is there any probabilistic intuition in your work, or is there probability?
Not much. It's very much analytical. It's very much analytical, and it has to go with there is statistics for sure, because it has to be averaging, and you have to average over all possible velocities and so to see it. But there is it's not really a probabilistic, and you really can have it deterministic equation. There has to be some statistics in the formulation. Here is I can give you an example. An analogy. Imagine that you have a race between horses on kind of circular tracks. So horses go there and there, etc., etc. And imagine they can run forever, and they start in a very ordered way, but they have different velocities, and their velocities are kind of not correlated. But there is a definite. They go at speeds which are independent of each other, really independent of each other, but not correlated. And you let them go. After a large amount of time, you take a picture. And because it's not correlated, you will see horses kind of everywhere. It will seem like dispersed everywhere, because the horses will have gone here and there, etc. So you have the appearance of equilibrium. But that is an issue about the point of view, because you see, the point of view that you see is that you cannot take into account exactly their initial position. You don't see it. And so in this model, you have apparent relaxation even in the absence of friction. Now imagine that you would put friction between the horses. Friction can be put in which sense? For instance, imagine each of the horses has, sticks extending left and right, so that they would be in the way of each other, etc. You let it go and run, and you would see after some time there would be kind of a rest, or they would all go at the same speed, they would all be together. It would be another kind of equilibrium. On that second one, you would have on that second dynamic, some notion of entropy, because there are collisions between the horses, they transform momentum, etc. So the relaxation there would be a consequence of the friction. It's a different mechanism. The first relaxation is not related to collisions, but because of the way that there is an apparent averaging because of the uncorrelation. And the second one is because of the friction. So these are two different mechanisms. In real life, there is a mixture of collision damping and collision-less damping. And Lyndon Bell was asking about the stability of galaxies. Certainly, it is much vaster than just the Landau damping. Landau damping is when you are very close to equilibrium. But also wildly non-equilibrium, in which you would expect it to occur. Nobody knows how to even formulate this for the moment in decent mathematical way. Some people have tried to do statistical physics on the configuration of galaxies and things like this. French mathematical physicist Robert, for instance, was very much into this and trying to put statistics on the set of solutions. But it's still widely open what would be the correct formulation on this.
Thank you. Any other questions? No? Okay, we'll continue tomorrow with Professor Villani's meeting at the Sofia High School of Mathematics with students, high school students. So let's thank our lecturer again.
Thank you.
Thank you.